Sean here from Armstrong Academy. In today's project video, I'd like to talk you through the design process and build of the fully 3D printed robot arm I can be seen playing with here, the Roswell. If you're interested in robotics, 3D design, coding, or general tinkering, you might find this interesting, so watch the rest of the video and feel free to comment. The robot here is the one you can pick up quite cheaply online called Emil. It's pretty easy to assemble and comes with an Arduino and all the necessary components, so users can program it to behave how they choose. This makes it a fantastic educational kit, and I use them quite often in my classes. However, they are quite flimsy and temperamental and can't lift anything much heavier than a felt tip pen, so I decided to design my own. After a lot of research, sketches, redesigns and complete fresh starts, I ended up using Fusion 360 to create this. I 3D printed it, put it together and wrote a test program, and, as you can see, it moved. The problem was that its performance was even worse than the cheap Me arm I had mentioned earlier. In hindsight, this was always going to be the case due to the added weight and friction of the large 3D printed parts, and the fact that I used the same cheap servo motors the Me arm does. Other than that though, I thought it looked great, and I knew that it would work better if I had better servos, so I went and bought some. I then started from fresh. I used the same schematic that I drew for the first version and built my 3D model around it. I decided to call it the Roswell because the McDonald's I saw on my visit to the city of Roswell a few years earlier was the inspiration for the design. One of the details I like most about the design is that all of the structural parts are 3D printed. Most of the parts can simply be clipped or screwed together. I also designed a matching controller. After I'd finished the design, I performed some motion studies on Fusion 360, testing that all the joints worked with the new dimensions. I then printed and assembled it, and wrote a basic code to see how it would perform. I then set about writing a much more complex code. My aim was to make it so that the user could use the controller joysticks to move the individual motors, and be able to record the positions with the touch of a button, then play back the recorded positions in a sequence. Programming the robot to do this without controlling the speed and with the servos moving one by one was relatively straightforward, but a smooth, controlled and direct motion from point A to B and C and so on was much more challenging. Now, the left joystick controls the rotation and the pivot arm, while the right one controls the backwards-forwards motion and the claw. Below are the play and record buttons. If the record button is pushed, the position is captured and stored. If two or more positions are captured and the play button is pressed, the claw will move from the first position to the next using the most direct path. It will then come to a stop. Further positions can simply be added to the sequence. If the user pushes the record button while the sequence is playing out, it will loop. This loop will continue until the record button is pushed again. The user can press and hold the play button to reset the sequence. The robot serves as a great demonstration of how automation is many times more efficient than manned robotics. It took me over a minute to get the ball in the cup, but it only takes the robot around 7 seconds. Moreover, it can repeat this action indefinitely. Here is a demonstration of a sequence with more steps. I spent many months on this project and it is finished for now. But there are many more things I would like to do with it in the future. For instance, I would like to improve its motion by using inverse kinematics and also add wireless control. But for now, that's a wrap. Thanks for watching. If you have any questions or suggestions about the project, leave them in the comments and I will reply. Bye.